Hey, our final keynote speaker for today is Ibrahim, or Ibi, Almufti from Arab, and he's with the San Francisco office. Ibi is a structural engineer, and he's worked on projects all over the world. I think he was educated at Berkeley, and comes to us from the great city of San Francisco. Yes,
Thanks, Carl, for the introduction, and thanks for giving me this opportunity. And thank you also to the audience and the other speakers. I was telling a couple people before the break that this conference, the spirit and the vibe of this conference is a lot different than what I'm used to. I'm used to being at engineering conferences where you stand up and you try and explain your technical research, and the job of the audience is to tear you down, basically. So this is a lot more fun, hopefully. Don't tear me down. So I was asked to speak about rebuilding, with the implication that rebuilding happens after disaster strikes. I'm going to cheat a little bit and frame the conversation or the presentation in a slightly different manner by arguing that we should be investing our time and money up front before disaster strikes. And I'm going to focus on earthquakes because that's my area of expertise, and I think there's a lot of areas of opportunity to minimize the risk due to earthquakes, and I think it might translate to other areas as well. So our Director of International Development at Arab is Joe Da Silva. And actually, just to give you a little bit of background about Arab, which is the company I work for, we're an international design firm with about 10,000 engineers, designers, consultants, with offices all over the world. I think we're in 70 countries. There's 10 offices in the US, and as Carl mentioned, I'm based out of the San Francisco office. So our Director of International Development, Joe Da Silva, was recently selected to give a very prestigious international lecture series called the Brunel Lecture by the Institute of Civil Engineers in the United Kingdom. And in the lecture, Joe says, I quote, because she says it better than I do, "The rapidly escalating cost of disasters is an increasing cause for concern for insurers, businesses, and governments. But the true costs of a disaster are felt most acutely at community level and are determined by the community's ability to recover and rebuild their lives. Investment in reducing the impact of natural hazards and in enhancing the ability of communities to recover is the most cost-effective long-term than dealing with the consequences of natural hazards." So the main point here is that we should be proactive and not reactive, and that's going to be the main point of my presentation today. So these are the costs of natural disasters over the past century. As you can see, they're rising. Joe attributes that to the trend of urbanization. So our cities are becoming increasingly stressed and increasingly vulnerable because of that. She calls the future risk of natural disasters an increasingly urban phenomenon. The insurance giant Swiss Re just said that 2011 was the costliest year on record for natural disasters. The Japanese earthquake alone cost about $210 to $300 billion. So can we reduce the cost of the impact of natural disasters by building up front, rebuilding up front? So like I said, I'm going to concentrate on earthquakes. The natural fear from earthquakes is that we're going to lose our lives in an earthquake, and that's because you see pictures of like this on television. Earthquakes represent about 4% of the natural hazards in the last decade, yet they represent or account for 60% of the natural disaster-related deaths. And that's really because earthquakes don't kill people. Buildings do. We are contributing to this as engineers, right? And we have an opportunity to do better. In the developing world, this is the issue, right? There's no codes, there's no oversight. This is a picture of a school that collapsed in Haiti. There's a lot of engineers focusing their efforts on this problem. In the United States, on the other hand, we actually do a pretty good job of protecting life. I'm going to spend a couple minutes on this slide. Is there a pointer, or can I walk out there, or is it too? Okay, so I'm just going to explain what the code intended performance objectives are in the United States, and I apologize if this is repeat for any of you. But basically on the left here, we have an earthquake intensity level, and it ranges from frequent to design level to maximum considered earthquake. In the US, we design for the design level earthquake, which has a 10% chance of occurring in the next 50 years, okay? This is analogous to the 500-year return period. If you read across the graph to figure out what the performance objectives are, and these are the performance objectives from operational to immediate occupancy to life safety to collapse prevention, we see that for a typical building, which is offices, homes, ordinary structures, the performance goal is life safety, okay? And then for hospitals or other essential facilities, the performance objectives are slightly higher, so in this case, immediate occupancy. So what does that mean? The Structural Engineers Association of California, I think, summed it up the best. And what they say is that the code intent is that it is there primarily to safeguard against major structural failures and loss of life, not to limit damage or maintain function. Okay, that's an important point. So that's how we are designing our buildings right now in the United States. So when we say that our buildings are being designed for earthquake loads, we're designing so that they maintain life safety, but we don't really care that much about how damaged they'll be. So what does life safety performance look like? This is a building in Chile, actually, which just went through the recent earthquake down there. This is the definition of life safety performance. The occupants were able to egress safely out of this building, but as you can see, there's quite a bit of damage there. It doesn't look like much, but actually this building is going to have to be demolished after the earthquake. This building is actually permanently tilting. You can't really see it there. It's tilting like 1%, okay? But it's so this is what we're designing our buildings for right now. So another point about this, my colleague who took this picture told me that the buildings down here, which were undamaged, had to be evacuated because the building just behind them, this one, was swaying about 5 feet in the aftershocks. So imagine that you've invested your life savings into an apartment or a home in the United States. I mean, this is what we're going for in the United States. I'm showing you the building in Chile, but this is what's going to happen in the US. Imagine if you've invested your life savings, you lose your investment, and you lose your place to live. You can't actually go sue a contractor or an engineer because actually we've met our obligations under the code, right? What does life safety look like inside of a building? This might even be more important, actually. The building contents and non-structural components account for about 80% or more of the total cost of a building. So even if your structure itself isn't damaged, if your non-structural components and building contents look like this, you've lost your investment as well. So we really need to focus on non-structural components as well. So there haven't really been many design-level earthquakes in the United States to speak of. Actually, the last design-level earthquake was probably the 1906 earthquake in San Francisco. Recent earthquakes, or not so recent anymore, like the Northridge earthquake and the Loma Prieta earthquakes were relatively minor in comparison. And they still resulted in some loss of life and some financial losses. So this has contributed to a false sense of security, I believe, that we have survived these earthquakes, so in that case we're going to be okay. Our buildings were undamaged in the Loma Prieta earthquake. Actually, a lot of the homes were not damaged in most locations. I know people in San Francisco that think like this right now. We survived Loma Prieta, we'll be fine. That's just not the case. This is a map showing, a contour plot showing the earthquake intensity, the accelerations of the ground measured from the Loma Prieta earthquake. They're very small, actually. This is the predicted earthquake intensities measured for a magnitude 7.2 earthquake on the San Andreas Fault, which has a 50% chance of occurring in the next 30 years. So this is an earthquake that's going to occur probably in our lifetime. And the intensity of this earthquake is about 3 to 4 times higher than the Loma Prieta earthquake. So the damage and loss associated with that earthquake is going to be much, much higher, and I'll show you that in a few more slides. So probably the best example from which to glean some information about post-earthquake recovery and rebuilding is in Christchurch, New Zealand, which is a modern city with modern building codes. Actually, a lot of people think that the New Zealand building codes are better than the US building codes in some sense. I just had dinner with someone who just got back from Christchurch on a reconnaissance mission. No, I don't want to do that, sorry. Oh, so let's go back. Okay. She just got back from Christchurch, and she told me that the downtown business district is still closed a year and a half past when the earthquake hit. She said that the rebuilding of the businesses are happening in the suburbs, and she doesn't know if they're going to actually rebuild back in the downtown. Okay, so this is a big problem. It might take years and years for Christchurch to recover, if it recovers at all. And I found this quote, which I thought was interesting, from Roger Sutton, who's leading the efforts, the Christchurch's recovery efforts. And he says, I quote, "The level of destruction that we've got there is such that we've actually got an opportunity to do something really fresh. And people are feeling optimistic now. What we had before was just mishmash from historical accident, so to speak. Now we can think about it much more carefully and do something much, much better." But the point is, we shouldn't really have to wait for the next major earthquake to make these changes now. There's two things that we can do right now to reduce the earthquake risk in the United States. The first, I believe, is that we've got to demand higher performance objectives from our new buildings. That means maybe rewriting the codes or convincing owners that they should be designing better buildings right now. And the second thing is we should be rebuilding now, retrofit aging infrastructure. The goal really would be to eliminate losses, essentially eliminate losses for new buildings in a major earthquake, and to minimize the losses as much as possible for existing structures. So I kind of mentioned already that the codes in the U.S. do a really good job of protecting lives. You know, we're going for life safety performance objectives. So really, we're more vulnerable to the economic losses from the direct damage from earthquakes to the building and the building content, and the indirect losses from things that are much harder to measure, like business interruption, loss of community, loss of quality of life. So we may be doing a good job of protecting our lives, but what kind of life are we going to leave for the survivors? And that's why I think we need to shift our thinking in terms of what's acceptable for new buildings, for performance objectives of new buildings. So I think that we should be doing better, and we can be doing better. This is a test that was done in Japan on a base isolated building. For those of you who don't know what a base isolated building is, it's basically a building that's supported on ball bearings. And so it decouples the ground shaking from the building. So if the ground's shaking really hard, the building's just going to be on top swaying really slowly. So it reduces the earthquake forces, accelerations, and displacements in the building considerably. So let me see if this movie works. Does the shake tape hold? Is it working? There we go. Oh. One. Okay. So on the left is the base isolated building. This is a hospital room. On the right is a co-designed hospital. It kind of gives you a good idea of the level of shaking that's going to be expected in a major earthquake and what could happen to the building content. So in Japan, actually, base isolation is very widely used. The 1995 Kobe earthquake really shook that society, and they really highly value earthquake protection. I think there's thousands of buildings that are base isolated compared to maybe a few hundred in the United States. So how do you get people to build better the first time? Well, I think first is you have to educate them. I don't think owners actually understand what they're getting from a code-designed building. The code intended performance objectives don't align with public perception, right? The public expectations. Once they are educated, I think they can make a decision for themselves on what kind of resiliency goals they want. And they might want to build better to preserve their investment, reduce their insurance premiums. Some of them are very interested in sustainable aspects, which I'll go into in a bit. And then the prevention of business interruption. There might be some additional incentives that a local jurisdiction could give. So for example, in San Francisco, they give you some zoning flexibility in terms of, let's say, building higher if you build it better the first time. There's also a chance to reduce things like property taxes to convince owners to build better. And I think eventually this is going to be mandated in the codes. Better building performance objectives are going to be mandated in the code. And we're probably 10, 20, 30 years away from that. The code's always way, way behind where the private practice is. So probably the most persuasive case for a building owner to build it better the first time is money, right? So in terms of preserving your investment, this is a study that my former professor at UC Berkeley just completed. It shows that for a code-compliant steel frame building, which was subjected to a design-level earthquake, there's actually a 25% financial loss associated with that. That's just a direct loss from the building and the building contents, right? And just to put that into perspective, at 40% is what triggers the building to be demolished. The owner will decide at 40% level that they just need to rebuild. So is that really good enough? I don't think so. The repair time associated with that is 3 months. That's the amount of time a contractor, once on site, will take to rebuild that building. The problem is, after a major earthquake, as we all know, it's going to be hard to line up financing. It's going to be hard to find a contractor. It's going to be hard to find engineers that are going to sign and stamp drawings. So this 3 months is going to extend into 6 months, 9 months, or years. On the other hand, if you base isolated that same structure, there's negligible financial losses, and the repair time gets reduced to about 2 weeks. And that repair time is really for non-structural components, like cracking of partitions, maybe a few ceiling tiles fell down. So you can resume normal business operations and at the same time have people painting your walls. So it's a much better solution to base isolate your building, for example, but there's other solutions out there. I'm just using base isolation as an example. So one of the major stumbling blocks actually is first cost. If you try to convince a building owner that they should be building it better, higher performance objectives, they normally equate that with newer advanced technology, and they equate that with higher first cost. Well, we have found that that's simply not the case. This is a base isolated hospital in San Francisco. It actually just finished construction a few days ago. In this case, the seismic forces get reduced so much, so significantly, that we're able to save about $10 million worth of steel from the superstructure. Now, this more than offset the cost of the isolators themselves and all the stuff that goes into the isolation system. So in many cases, it's actually cheaper to build better. Even if it was more expensive to build it better, we also, I think, need to put that in context of how much the overall project costs. Typically, an owner is deciding not to base isolate a building because it costs an extra 1% or 0.5% more to build it with isolators. So they really need to think about it in terms of the life cycle cost of the building. So the business interruption case is kind of harder to measure, but I just want to give you an example of this. I'm going to read this so I can get all the details right. But building it, this is an example of where building it beyond code resulted in speedier recovery to business. So this is a case of 2 different car manufacturers in Turkey, which were subjected to the 1999 Kocaeli earthquake there. And this is a report that one of my colleagues put together. So he says that one car manufacturer, Ford, an American company, appointed a local engineering firm to design their facility in Turkey in accordance with the local seismic code, satisfying the necessary requirements for life safety criteria. It did not collapse when the magnitude 7.6 earthquake struck in August 99, but there was considerable damage, particularly to the non-structural elements, including equipment, which were not covered by the engineer's scope of work. Operations ceased and the plant was eventually closed down. In contrast, a Japanese manufacturer who understood seismic risk much better design their facility, including the equipment and non-structural elements, to exceed code requirements, to incur minimal damage in an earthquake. The facility performed as expected, and operations could have resumed immediately. However, the factory remained closed for several weeks as most of the workforce lived in housing which collapsed or was badly damaged, causing deaths and injuries. Yet after a short while, the employees were able to return to work and begin to rebuild their lives, helped by the fact that the factory was still able to operate and they had retained their jobs. There's also a case for insurance. You know, the benefits of earthquake resilience on insurance costs is rarely realized. We have done studies to show that earthquake resilience or improvements in earthquake resilience of, for example, in this case, a global manufacturing facility could reduce earthquake premiums. In this case, it reduced the earthquake premiums by $460,000 a year, and it cut the level of insurance from 80 million down to 40 million, just because we were doing some site-specific technical resilience analysis on this site. Are there any architects in the room? A few. So, you know, right now the trend is sustainability. I mentioned before, 80% or more of the total cost of a building is in the non-structural components and the contents. And for sustainable building owners, they throw a lot of money at highly sustainable materials and high-performance architectural systems and mechanical systems. But why would you put those kinds of systems in a co-designed building, which will just, you know, be severely damaged after an earthquake? So all those components that you spent a lot of money on and invested a lot of money on are going to go into a landfill. So is that really the way we should be building these highly sustainable buildings? So we really need to think about resilience and sustainability in the same light. So there's really a lot of reasons why a building owner may decide to build it better the first time, to beyond code performance objectives. This is an earthquake resiliency rating system that we've been developing for the past 6 months. And it's a way of trying to communicate to an owner what they're getting from a co-design building and what they could get once they decide, based on their risk tolerance, what kind of resiliency goals they want. So for example, you can't read it, I don't think, but this bar right here says a code-rated building, a code building. For a design-level earthquake, the code-rated building gives us significant damage, significant financial loss, and significant business interruption. This is that building in Chile I was showing you. So we can educate the owner simply by telling them what they're getting with a code minimum design. We could also say, hey, we can get you something much better. This is a platinum rated building, gold rated, silver rated. So for a platinum rated building, the losses are negligible. We actually say that for a platinum rated building, the financial losses should be about 2% or less. So these are terms that an owner can understand, dollars and downtime. You know, as engineers, we've been terrible at communicating this before. We always used to talk in terms of life safety or immediate occupancy, and no one really understands what that means. How am I doing on time? Yeah? Okay, so shifting gears just a little bit now into rebuilding now. I wanted to focus on San Francisco because I think San Francisco has done a really good job of increasing their resilience goals and retrofitting existing buildings to increase the resilience of the city. San Francisco sits between two major faults, the San Andreas to the west and the Hayward Fault. Hayward Fault actually runs through Oakland and Berkeley. So the USGS predicts that a magnitude 6.7 earthquake will occur. There's a 63% chance of a magnitude 6.7 earthquake or greater in the next 30 years. There's actually a 50% chance, as I told you before, of a magnitude 7.2 earthquake or above occurring in the next 30 years. So this is going to happen. So this is a quote I found from National Geographic. The morally right thing to do once you've identified a threat of this magnitude is to be prepared. It's like earthquakes in San Francisco. Not preparing for it has intolerable consequences. This is from an article I was reading about solar flares, which apparently we should all be very worried about. It's pretty scary. So the implication here is that we're prepared in San Francisco. right? We've identified the threats. You know, we tell everyone there's a magnitude 7.2 coming, and we've actually prepared. The truth is we're not prepared, and here's the proof. This is a study done by the Advanced Technology Council in conjunction with the Community Action Plan for Seismic Safety for San Francisco, or CAP. So this is the magnitude 7.2 earthquake, 50% chance in occurring in the 30 years. That's a 43-year return period earthquake. So it's a good chance of occurring in our lifetime. So basically this is showing considerable losses, considerable direct losses, 34 billion in this case. And actually they can't even measure the indirect losses. It's really impossible to measure the indirect losses. They say 10 billion plus caveat, caveat, caveat. We can't measure these other things like business interruption, people leaving the city, et cetera, et cetera. So this is pretty scary. This is what will happen if we don't take any action. I mean, I think in the report it said that it would take San Francisco about 10 years to rebuild from this earthquake. So the CAPS report actually didn't explicitly assess the damage to tall buildings. So we actually recently... Did I do something? Catastrophe. I think I'm still okay on time. I only have I think I only have 5 more slides or something. Yeah. I've got some cool videos though. Well, let me just finish this slide at least on tall buildings in San Francisco. We just recently concluded a study of these tall buildings in San Francisco, which are really densely clustered together. And most of them are built in the 60s and 70s and 80s. They're steel frame construction. These are a particularly vulnerable subset of buildings because they were designed, first of all, to older codes, and they actually had pretty poor construction detailing of all the connections. So we really are worried that in a major earthquake, these might collapse. And I forgot who the speaker was who was speaking about the World Trade Center, where it was designed to fall like that. I don't know if it was Van. But in an earthquake, that's not how a building would collapse. The building collapses like that, and it's going to collapse on other buildings. So this is a real threat to the resilience of San Francisco. And then my next slide is a video showing. Yeah.
San Francisco has, in a short way, shallow earthquakes.
Yeah, shallow crustal.
If you look at Seattle,
Yeah.
that's close to my heart.
Yeah.
Waves are entirely different. Can you talk something about tall buildings
Yeah.
in both areas?
Definitely. Seattle actually has 2 types of faults. There's one that runs through called the Seattle Fault. There's actually 3. There's a Seattle Fault that runs through, that's like the San Andreas. There's another fault called the Benioff, which is kind of way under. And then there's a subduction zone, Cascadia, way off the coast. And that's the same type of fault that produced the Tohoku earthquake in Japan. That earthquake is what people are most worried about because it can produce a magnitude 9. And that magnitude 9 occurs every 500 years, like historically. It's shown in the records. I think it's been 1700 or so was the last one where that one occurred. The problem for tall buildings in Seattle due to that earthquake is very significant because that earthquake will probably shake the Seattle basin for about 5 minutes. So for tall buildings, especially steel, well, concrete too, if you've got 5 minutes of shaking, you actually get fatigue of your connections, which make it even worse. And they predicted a lot of collapses. There's a study by Tom Heaton at Caltech that did that. I can refer you to that report. Okay, so thank you. So we did some studies on these tall buildings, subjected them to major earthquakes to see what would happen. We did several analyses, and here is one example of one of the scenarios that we ran. In this case, the building doesn't collapse. The building, though, has a significant permanent tilt. We're not magnifying that. You can actually see that. That's about 5% tilt. This is indicative of what would happen, I think, with most of the tall buildings in San Francisco under a major earthquake. So you've got about 5% permanent drift. You cannot reoccupy that. You can't rebuild it. You'd actually have to tear this thing down. So imagine if even 1 or 2 or 3 of these buildings would have to be torn down. There's also some scenarios we ran where the building actually did collapse. So like I said before, 1 building collapsed in San Francisco. It's densely clustered downtown. How do you rebuild from that? We've really got to start looking at retrofit strategies for these buildings. So the good thing is that we are looking at retrofit strategies. We're going to be doing stuff over the next 30 years. CAPT has a 30-year implementation plan, a policy roadmap. This isn't an overnight solution. This is going to take decades. They've already retrofitted almost all of the most vulnerable buildings in San Francisco, which are the unreinforced masonry buildings. There's about 1,600 of those. And then there's going to be mandatory retrofits to wood frame buildings that have soft stories. Soft story buildings, for those of you who don't know, are multi-unit apartments basically that are built over a garage. And the garage has no, if you take out that hole, there's no strength on that face. And so basically the building would just collapse on itself on top of the garage. So there's going to be mandatory retrofits, which would substantially reduce the losses that I showed in the slide a couple slides ago. And based on the research we just did, we're going to prioritize our tall building retrofit strategies. I met with the director of the Pacific Earthquake Engineering Research Center a couple of weeks ago, and they're going to be putting a lot of money into looking at this problem. And the Building Owners Management Association is also very interested. I've just got 2 more slides here, 3 more slides. So let me give you an example of a building that was retrofitted, an example of before and after. This is the case of the Washington Hospital. It's built in Fremont, which is right next to the Hayward Fault. And the Hayward Fault is capable of producing a magnitude 7 earthquake, and this is what the waves might look like. The magnitude 7 earthquake hits Hayward every 140 years. It's been 144 years since the last Hayward earthquake. So there's a lot of buildings, like I was saying, in San Francisco that have been retrofitted, the unreinforced masonry. This is an unreinforced concrete building. I mean, it's lightly reinforced, let's put it that way. It's not unreinforced. This is a hospital that's in operation. Actually, I should have taken the name away, but anyways. This is what it looks like subjected to that earthquake. So you can't, the analysis actually can't even go that far because it's basically, this is collapsed. It's collapsed at the 2nd story. And this is not unexpected. We expected this to happen. It's a lightly reinforced building. So what happens if you base isolate it? So this strategy is basically cutting the foundation at the base and inserting the base isolators. This is the same strategy that was used on the San Francisco City Hall and many other buildings actually. The Utah State Building, I think. Same earthquake. It basically performed perfectly. No damage. So that's the kind of technology we have today to do better, right? Retrofit our aging infrastructure. So we should be rebuilding this type of infrastructure now. So in conclusion, in the developing world, the problem isn't easy, but at least we've identified what the problem is. There's no codes, there's no oversight, the construction methods are pretty poor. In developed countries such as ours, I don't think the code goes far enough to protect our investment. So we really need to try and change that way of thinking. So let's invest now to reduce our rebuilding and recovery efforts at a later date. Thank you.
Thank you. think we have time for a couple questions. Any questions? Yes.
Yesterday in one of the classes. It sounds like there's no governing power to that international code. Am I correct?
Governing power? I mean, each jurisdiction, let's talk about the U.S. The U.S. adopts certain things. So the International Building Code adopts, I mean, it's really complicated, actually. There's something called the ASCE 7, the American Society of Civil Engineers, which governs the loads on the buildings, and the local jurisdictions adopt that. The International Building Code can be adopted by whoever wants to adopt it. It's just out there. But it's a little more complicated than that. I didn't hear that. Yeah.
You talked a little bit about mandatory retrofits in San Francisco.
Yeah.
And I was wondering if, and to get at sort of the policy side and the planning side, can you talk a little bit about what triggers the retrofits?
Yeah.
In terms of, I can understand government buildings, those things, but
Yeah.
the private homes and everything, how do you is it through permit requirements? What's your thinking on that?
Yeah, there's a period where they're going to do voluntary kind of retrofits, and there's like a grace period, but eventually it's going to be mandated by the city. Like you're going to have to retrofit this building. So it's simply a mandate.
But if somebody is coming to do that, if they're not buildings, or if they're not coming in for...
Oh, these are existing buildings.
Yeah, so if they're not coming in to put in like an addition on...
Yeah, it's not a triggered thing. I mean, if you live in a building that has a soft story, yes. And that's because there's the local government there is really taking this seriously. I mean, I don't know if I think San Francisco is pretty unique in that regard. There's enough people in San Francisco that understand the risk, and there's enough people pushing the policy that I think it looks like it's going to be adopted.